Alright, hi everyone. So welcome to the second lesson for our topic 7 vectors in pure maths 3. So let's start with the learning outcome. Alright, so in today's session, we are going to learn how to use formula to calculate the scalar product of two vectors and to use the result to help us to solve the problem involving lines and points. Okay, so in short, I just want you to remember the keyword here, which is scalar product. So the main focus of the lesson is to expose you to what is the definition of scalar product and what are the two formula that you use to calculate this scalar product. So for the more application part, we'll be able to actually see more questions when we try to discuss more content in future. All right. So for today's session, you are just going to know what is it meant by scalar product. All right, so let's start with the introduction. All right, so in previous lesson, we know that there are different kind of like operation that we can carry out in vectors, right? For example, we have learned like how to do the addition for the vector, then how to do the subtraction for the vector, and also the last one when we talk about the concept of like parallel line, we also know how to do what we call as the scalar multiplication, which is that we multiply the vector with a scalar. Okay, so in today's session, we are actually going to look at a multiplication, but then it's not between a scalar and a vector, but it's between a vector and a vector. So in short, right, meaning that we learn how do we multiply two vectors together. All right. So in vectors, there are actually two types of multiplication in that actually give us two different products. So for the first one is what we will learn in this lesson, which is called as the scalar product. Okay, so sometimes this scalar product is also known as the dot product. Okay, but in your syllabus, the word that they try to use is scalar product lah. Yeah, but when you try to look at like some reference online or in your textbook, they try to use the word dot product as well. Okay, so which means that when we try to denote it in like a symbol form, then the way that we'll be writing it is like A dot B. Yeah, so if you know that the dot here actually means times also. So normally when we try to do scalar product, then we will do A dot B. Alright, so for this kind of multiplication, the product, meaning that the result that we will get out from the multiplication will be a scalar. So which means that it's going to be a ordinary number. It's like a normal number. Okay, so the second type of multiplication, which we are not going to cover in our A-level syllabus, which is called as the vector product. Okay, or sometimes it is also known as the cross product. So normally for this second type of product, right, we'll try to denote it like A times B. Okay, and the product that you will get, it will be a vector also. So which means vector multiply vector, you get a vector. Okay, so but this content will be involving like knowledge of matrices and so on, which in your syllabus of P3 we actually didn't learn this. Alright, so this is like just information for you. Yeah, in case that you feel like how come like when you try to search it, then you feel like got two types of product. Yeah, so there are two types, but in our syllabus, we actually only learn the first one, which is called as scalar product. All right. Okay, so today we are going to look at two definition of scalar product. So the first approach will be in a form of geometric form. Then the second one will be in terms of algebraic form. Then at the end of the lesson, we are going to combine these two ideas together. Then we are going to solve some examples. Okay, so let's try to look at the first approach here, which is the scalar product for geometric form. So I'm going to explain this idea by using a simple illustration here. So this is a diagram that a person is trying to pull an object along this surface by using a rope here. Okay, so if you learn physics, right, for us to calculate the work done by the person, it will be using the formula of the force needed for the person to pull the object, then multiplied by the distance that the object moved. Okay, so that's the idea. So when we try to look at the diagram here, you would realize that the direction of the person pulling the object, right, is not the same with the direction that the object actually moved. So when we try to think of it in this way, we can understand that not all the force that used by this person to pull the object is actually moving, is actually causing the object to move. Okay, let me try to rephrase in another way, which means that only some of the force that the person used to pull the object actually make the object move because of the angle here, right? So which means that the force that really caused the object to move is the force that left after we try to get rid of the constraint of the angle here, which means we need the force in the same direction as the distance of this object move. Okay, so we are going to calculate it together. So if let's say when we try to calculate by using the formula, it will be work done equal to force multiplied by the distance, right? So for the distance, it will be quite easy because if let's say it's represented by the vector b, right? So the distance that the object b move is eventually going to be the magnitude of b lah. Okay, now the problem is A. Because the force that actually caused the object to move, it will be in this direction as well. It's not in that direction. If in this direction, then we can straight away use magnitude A. But the force and the distance has to be in the same direction. Okay, so how are we going to do that exactly? So we can try to understand it in this way. So if I have this vector, which is A, right? Then I have this, which is the direction of the force that I actually want. Okay, so we try to denote the angle here as theta. Alright, so we can try to draw a right angle triangle here. So if we try to get rid of the idea for the direction here, we only want the magnitude of the force, then what are we going to do? We are going to do the magnitude, the modulus for A. So it represents the magnitude of the vector A. But now we need the force in this direction. So by using SOHCAHTOA, we know that this will be our opposite. Then this is adjacent and this is going to be hypotenuse, right? So if we want to find the force, which is the A, then we have the H, which means we need to use cos. So which means cos theta will be equal to modulus will be equal to the force, yeah, A first, right, cos sine CAH. So force over hypotenuse, which is modulus A. So if let's say we want to find the force, then it will be equal to modulus A multiply cos theta. So now we try to put into our formula here. So the force will be equal to theta A modulus A cos theta, then multiplied by the distance, which is the one that we said, the magnitude of B. So when we try to combine these two together, so which means that it will actually become modulus A B then times cos theta. Okay, because it's just multiply, right? So no matter how you arrange it, it will be just the same. So the work done is the force multiplied by the distance, right? Which means it's the vector of the force, which is A, then multiply the vector of the distance, which is B. So this is our first definition for the scalar product of two vectors. So we try to write it here. So which means that A dot B is equal to modulus A multiply modulus B and multiply cos theta. Alright, so this formula actually allows us to calculate a value that represents the impact of one vector on the other. So which means that when we try to multiply them together and to get a product, we actually take into the consideration of the magnitude by using of the magnitude here, and also the direction of the vector by using the theta here. Okay, so because we know that vectors involve both direction and magnitude, right? So when we try to multiply them together, we need to take into consideration of these two components. So we have magnitude here and we have direction here. So to make this clearer, right, you might want to just write down because you have a theta here, then how is the theta here defined? So the theta here is the angle between two vector. So you might ask, I have two vector here, so is it mean that no matter how is my arrow, as long as the two vectors intersect, then that's the angle between it? No. So you must remember that the theta, it must be either the two vector going out at the same time, or in the other word, so we know that if we try to expand this, then isn't it this will actually be the same theta as well. So which means that you have the first idea, which is the angle must be from a vector that going out from the intersection point. So the other case will be, or you have two vector that moving in the intersection point is the end of the vector going in. Okay, so I'm just going to erase this and redraw it again. So the theta, it can be either the two vector going in or the two vector going out. Okay, so both idea you should able to get the answer, but it's just that it cannot be like one going in then one going out like that. So it must be both going in or both going out. All right, so we'll try to look at the first example. So to just introduce to you like how do you use this formula. Okay, so let's look at example 1. Alright, so given the vectors P and Q and the angle theta between the two vectors is 45 degree, so find the value of the scalar product. So we can try to write down our formula that we learned just now. So A dot B equal to modulus A multiply modulus B and then cos theta. Okay, so which means that we might need to find the modulus first, which means the magnitude of the vector first. So let's start with the first one. So the magnitude for the vector P is equal to 8 square plus negative 6 square plus negative 10 square. Okay, so from here, then I'll be able to get my answer. It will be 10 then square root 2. Okay, you'll just use your calculator to solve this. Then modulus Q will be equal to, so same thing, modulus. So 4 square plus negative 3 square plus 0 square. So for this one, then I'll be able to get square root 25. So which means it's going to be 5. So now we can try to substitute them in the formula. So B P dot Q, the scalar product, will be equal to the magnitude of P, so which is 10. Yeah, if you want to copy down the, what is that called, the formula, yeah, you can try to apply it first. So PQ, then cos theta. So which means in this question, then it will be 10 square root 2 multiply, so with 5, then after that cos 45. Alright, so you can just press everything in your calculator, then you'll be able to get the answer is 50. Okay, as simple as that. Alright, so let's continue the notes. Alright, so just now we have learned the first definition of the scalar product, which is the geometric form. So now we are going to look at the two special cases under the geometric form. So the first one is what we call as the parallel vector. So if let's say we have two vectors, which is A and B here, and they are parallel, which means that they have the same direction, right? So if let's say the vector has the same direction, then what is the angle between these two angles? So it will eventually be 0. Okay, if you can't understand that, let me try to explain like this. If let's say I have a vector like this, then I have the other vector like this. So the angle between them, then I'll try to draw it like this, right? So going in, then going in. So the angle between is like here. Or if you want to do it like is in the case of going out, then which means it will be like this. Then after that, the other vector like this, then going out, then this is the angle in between. But they will be the same. But if let's say now the vector is parallel, then when you try to draw the vector together, then when you try to put them together, right, then the angle between them will be none. You get what I mean? So that's why the theta between the two parallel vector will be a 0 degree. So when we try to use calculator to solve, or if you remember some special angle, we know that if the theta is 0, then cos 0 is actually equal to 1. Okay, so from that, if let's say the cos theta is 1, right, what happened when we try to do the scalar product? It will be modulus A multiply modulus B then cos theta, right? But now cos theta is 1. So which means that what do we left? So it will be modulus A multiply modulus B then multiply by 1. So after that, my answer will left with modulus A multiply modulus B. So which means I do not need to do the part for cos theta because I know that that's going to give me 1. So we know that if the vectors are parallel, then A, the scalar product between the vector A and B will equal to the magnitude of A multiply the magnitude of B. So which means that if you have the case of the vector multiplied by the vector itself, right? So which means that if I have A multiplied by A, then what do I get? Yeah, then I will get modulus A multiplied by modulus A lah. Then because of course if the vector is the same, right, which means that they are parallel. So the modulus A multiplied by modulus A, which means I'll get modulus A squared. Alright, okay, then after that, the second special case will be for the perpendicular vector. So if the vectors A and B are perpendicular, like what you can see here, so they are going out, so which means this is like the angle between them, so which is 90 degree. So the cos theta is equal to cos 90, and we know that cos 90 will give us 0. So if that is 0, so which means that when we try to do modulus B modulus A multiply modulus B, then cos theta is going to give us modulus A modulus B multiplied by 0. So what is our last answer? It will be 0. So if the vectors are parallel, which means that the scalar product of the vectors is going to be 0. Okay, so this is the special case will be very helpful for us to solve some coordinate geometry questions later, so you might want to remember. Alright, so before we move on to like the second part, which is the scalar product for the component form or in the algebraic form. So let's try to do short properties of like the scalar product. So if let's say we have a scalar product of A dot B, the answer will be the same if we try to do B dot A. Okay, so yeah, the idea is when you do modulus A multiply modulus B multiply cos theta, right, it's the same when I try to put modulus B first. Like A times B or B times A is going to give me AB or BA, but the last answer is actually the same. Okay, so this is like the commutative law in mathematics. Then this is like the scalar. So which means that it's the same thing if let's say I have 2 times 3, then if let's say I try to put a scalar in front, so it doesn't matter that the scalar going to multiply which one. So it's going to just give me the answer when I try to do the scalar for A. Or it will be the same thing also if I try to take out the M, then I will do the A dot B first. It's just going to give me the same answer. Okay, so after that, for this one is like the distributive law in maths. So yeah, this is the same thing like how you normally expand a algebraic expression. So this will be A, then yeah, times B, then after that plus A times C. Oops, I'm sorry. Times C. Alright, so just like expand it like normal. So for this one, yeah, it's like normally your quadratic expression, right? Yeah, so it's the same thing as well. So it will be A dot C, then plus A dot D, and then plus B dot C, and then plus B dot D. Okay, the same thing like how you expand lah. So this one multiply, then this one multiply, then B multiply, then B multiply D. So this is the distributive law. So it fits also in like a normal form. All right. So now we'll be using like the distributive law here or some properties here to actually help us to look at the second definition for a scalar product, which is in a definition for like the algebraic form or like the component form. Okay. So the idea here is normally it's not easy for us to actually know the angle between the two vector. So it will be not so convenient if let's say we need to work out the scalar product by using the geometric form because we need the angle between the two vector. But in a much more practical way, normally we have the vector in terms of like the component form, which mean like they tell you that what is the ijk thing, yeah, the component. Okay, so now we'll be looking at another alternative to calculate the scalar product, which by using the component form, which means if I know what is the vector, then I can straight away solve for my scalar product already without knowing my angle. So this is the second formula for scalar product. Okay, so let's try to derive the formula by using something here. Okay, so if let's say the component form for vector A is A1I, A2J plus A3K. Then the same thing for B, you have B1, B2, B3 for IJK. Okay. So if let's say we try to do the A dot B thing, right? So what happened is actually it means that it's like A multiply B, right? So let's try to put them together. So A1I plus A2J plus A3K. Yeah, we are going to use like a three-dimensional component form because it will just apply the same thing when we try to use it like two-dimensional. Yeah. Okay, then the second one will be the B1I, B2J, and the last one is B3K. Okay, so when we try to multiply, then this will be the same thing like we do the distributive law just now. Okay, so we'll try to expand it like how we expand a normal algebra expression. So A1, this is 1, sorry, A1I multiply with B1I, right? So what we get? We get A1, B1, and II. Okay, then after that, the second one, so A1I, then the first one, then we go to the second one. So when we multiply, then we get A1, B2, then I and J. So we continue the next one, then it will be A1, B3, I and K. Okay, now we continue for the second one. Perhaps we try to write in the second row so it will be easier for us to look at it later. So A2, okay, then when we multiply, then we have A2 B1 is going to be IJ. Yeah, so it's JI lah, but I'm just going to write it in IJ so it's easier for us like for the tidiness. Then A2, then multiply with the second one, we have A2 B2, so this part is JJ. Then the next one is going to be A2, B3, then J and K. So we continue for the third part here. So what we get? A3 and then B1 and IK. So continue for the next one. A3, B2, and this will be J and K. Then the last one, we have A3, B3, and then K and K. Okay, now how are we going to simplify this thing? Okay, so you see, now we are going to use the special case that we learned just now already. So since that I is parallel to I, J is parallel to J, right? Then K is parallel to K. So when we try to multiply I together, J together, and K together, what do we get? So we need to go back to the just now that one. You remember, if let's say they are parallel, so which means A times B will eventually equal to modulus A multiply modulus B. So which means that in this case, we know that when I and I multiply, I will actually get modulus I multiply modulus I. So J and J multiply, then I'll be able to get J modulus J and modulus J, right? So same thing, if KK, so I'm going to get modulus K multiply modulus K as well. So what is the, when we try to do like this, which means it's the magnitude, right? So what is the magnitude of I? So we know that I, j, k are all unit vector. So if they are unit vector, meaning that their magnitude is actually 1. So that's why 1 multiplied by 1, what do you get? You get 1. Then j, which means it's 1 also. So all of this actually will give you the answer of 1. So later we are going to substitute all the I, j, and k to become 1. Okay, then the next one. So we know that IJK we talk about, like if let's say you have here is the, normally this is the J and this is the K, right? Sorry, this is the I and this is the K. If let's say it's a 3D lah, so they are always like 90 degree to each other. So if they are perpendicular to each other from the concept that we learned, yeah, what do you know? So if they are parallel, when we try to find the scalar product, it will be equals to 0. So which means that for all the I j, or the jk, or the ik is going to give us 0 because of they are perpendicular to each other. Okay, so now you can imagine that all the ij, ik, ij, jk, ik, jk here, yeah, is, I think I left out here, maybe I still have ij, ik, jk, I wrote already, ij, and one more is ik, yeah. So all of this will give us 0. So we know that if we try to continue for this part, so ij here is going to be 0. So no matter what you get from a times b, right, when you multiply by 0, it's going to give you 0. So this part, this part, this part, and this part is going to give you all 0. So I'm just going to like draw it here. Okay, ij, ik, jk, ij, ik, and jk is going to give you all 0. Then after that, for the part of the ii, jj, and kk is going to give you 1. Okay, so now let's try to put it in like the summary here. So which means that when a times b, then what do we left? We left with the orange color here, right? Then let's try to change I is like become 1. So which means a1, b1 multiplied by 1. Then after that plus, so this becomes 0 already, 0, 0. So I left with this. So you can see it's a2, b2. So a2, b2 and multiply by 1. Then after that, the last one, what do I left? So here 0, 0, 0, and this one I left with a3, b3. So a3, b3, then multiply by 1 as well. So when we try to simplify it, then what you can see, when we multiply by 1, then you get back the same thing, right? So that's why a dot b is actually equal to a1 multiply b1 plus a2 multiply b2 plus a3 multiply b3. Okay, so let us try to write inside here. So which means the algebraic definition, so which means if let's say you do not have the angle in like a geometric form, so how are you going to find the scalar product? Is by using the algebraic form, which is the vector A multiplied by vector B will be equal to A1 B1 plus A2 B2 plus A3 B3. All right, yeah, this is for if let's say the unit vector that you are going to if you are using a unit vector here, which is ijk. Okay, so when we try to combine the both definition that we learned for the scalar product, right, then what do we get? We get that a dot b, the scalar product for the vector a and b, is equal to modulus a multiply modulus b cos theta equal to a1 times b1 plus a2 times b2 plus a3 times b3. So this is a very useful formula, and as it will actually help us to find the angle between the two vector if we know the component of the vector. So which means if let's say you are given the component for the angle for the vector, right, you can find out this part already. Then obviously you can find out the magnitude also. So by substitute this part, then you will be able to solve for the angle between the two vector. Okay, so yeah, this formula will be the only formula that given for your vectors. So yeah, this will be given in your examination formula sheet like exactly like this. All right, so you can see that if vector A is AI, A1I, A2J, A3K, then B is this, then this is like the formula that we write just now lah. Okay, so now we'll be looking at like few simple example here, then so that you can understand like how everything works. Okay, so let's try to look at the example. Okay, so example number one, the vectors OA and OB are given in this. Yeah, then calculate the scalar product. Yeah, so number one and two is basically to expose you to the second formula that we have learned just now. Yeah, so yeah, this is an example of the question that you need to find the scalar product without knowing what is the angle. So the only approach that we can use is by using the algebraic form. Okay, so that's why we have AO and OB, right? So which means that AO dot OB, okay, will be equal to, and what is your A1 multiplied with B1, and then plus A2 multiplied with B2, and plus A3 multiplied by B3. Okay, so A1 and B1 is basically like your first your first vector and the I part, then after that your first vector, the J part, and the second vector, the J part, and A2, B2. So it will be like quite easy to see when the question trying to give you in a form of like unit vector. So basically it's like 3 times 6. Yeah, so which means it's the I component multiplied together, then plus the J component multiplied together, then after that the K component multiplied together. Yeah, just like that. Okay, so it will be equal to, so we have 18 and plus 1 minus 10. Okay, so do I do something wrong? Oh, sorry, this is -4, so 4 here. Yeah, okay, so this should be plus 4. So 22 minus 10, so I have 12. Yeah, so just like that. All right, so after that, we are going to look at question 2. So the position vector of point A and point B relative to an origin is given by this. Yeah, so this will be quite easy as well. Yeah, so this is in unit vector ijk. So which means it's the exactly same thing like the question 1, but it's just that this is in the form of ijk, and question 1 try to give you in the column vector form. Okay, so the first component, the I part multiply the I part, so which means 2 multiply 3. All right, yeah, if you want to write down the, what is that called, the formula, then you can try to write down first. So A1 times B1 plus A2 times B2 plus A3 times B3. So if let's say this is a 2D question, which means you do not have the last part lah, but you are just going to get do the same thing. So A1 B1, so it will be 2 multiply 3, and then plus P, the B2 is -1, then plus 3, then P. Okay, so just solve them. So 6 minus P plus 3P. So from here, I'll get my answer 2P plus 6. All right, yeah, as simple as that. So let's move on to the next one. Okay, so number 3 here. Yeah, so vector P equal to 8i minus 6j minus 10k, and given Q is 4i minus 3j. So show that the angle theta between the two vectors is 45. Yeah, so this is one of the application that I mentioned just now. So if let's say you are given the component, then how are you going to use the combination of the two formula to help you to get to the answer? So which means the first one, perhaps we can try to find the scalar product first. So PQ will be equal to, yeah, so the first component multiply, so I and I, so 8 and 4. All right, and then plus then j and j, so -6, -3, and plus -10. And don't forget, you don't have anything here, right? So which means it's going to be 0. Okay, so from here, then I'll be able to get the scalar product of these two, for these two vector will be equal to 32 plus 18, so that's why 50. All right, so now we will need to try to equate them to the modulus P multiplied modulus Q multiplied by cos theta. So let's try to find the modulus for P first. Okay, so we have 8 square plus negative 6 square plus negative 10 square. Okay, so from here, then I'll be able to get 64, 64, 36, then 100, so which means I'll get 200. Okay, so if you want to change it, then it might be, 10, then square root 2. Alright, then after that for the Q, so we try to do the same thing. So you have two component only, so which means 4 square plus negative 3 square. So 16 and 9, so which means 25. Sorry, this is equal to. Alright, so square root 25, then it will be 5. Okay, then after that, let's continue that. So which means that P, Q should be equal to modulus P multiply modulus Q cos theta, right? So the cos theta is what we want to solve in this question. So we have got this answer from here. So 50 equal to, so 10 square root 2, 5, and cos theta. So let's try to rearrange the whole thing. Then I will have cos theta will be equal to 50 divided by 5 times 10 square root 2. Okay, so when I try to simplify, then I'll be able to get square root 2 over 2. So shift cos your answer, then you will be able to get theta equal to 45. So this is how you show. Alright, so yeah, I hope that you are following. So basically this questions, right, is for you to you can compare to the example one we have. Oh, I'm sorry. Now I realize that maybe my question number here is wrong, right? This should be question 4. Yeah, sorry, because I changed to another Word file. Maybe when I copy, then the question here, the number is like a little bit run off. Yeah, but it's the same thing. So this is the question that I want to show you when you try to compare to your question 1 just now. So yeah, your question, the example 1 that you did just now. So you can see that the P and Q is actually the same thing, then equal to the theta is 45. So this is like one of the method that to show you that no matter you are using the component form or you are using the geometric form, it's actually giving you the same answer. Okay, so that's why when you try to solve this, then you realize that how come the number is like so familiar. Yeah, so because it's the same idea like just now, but just now that one is like given you the angle already, then you straight away find the answer, the 50. But this one is how are you going to use the component form and to show that it's 45. Alright, so let's try to move on to the number 5. Yeah, so sorry, this should be 5, right? So which means just now it's like 2 and 3. Okay, so A and B. So find the value of P if you know that the vectors of these two vectors are perpendicular. Yeah, so this will need to use the special case just now, as we know that if let's say the two vectors are parallel, right, which means that we know that the scalar product of this vector is going to be equal 0. Okay, so equals to 0. So we can straight away solve for the scalar product here. So I and I, so which means it's going to be P times 2, then plus, yeah, so don't miss out, like you don't have a J here, so you don't like use the negative 3 multiply the J, yeah. So you have 0J, then after that 1J, then plus negative 3, and then 5. Okay, so equal to 0. So from here, I know that 2p equal to 15, and I'll be able to get that p equal to 15 over 2. Okay, so continue with B. So you need to show that the two vectors here are perpendicular. Yeah, so please remember, so yeah, like for the question of show that, so which means you cannot do it like the A part that straight away write that scalar product equal to 0, because if you already stated that scalar product equals to 0, then what's the point that you want to show here? Okay, so which means that in this case it's going to be you calculate the scalar product, then you show that the answer is equal to 0, so that's why it's perpendicular. Okay, so the scalar product will be equal to, So I and I, so which means Q multiplied by 1, and then plus -1 multiply Q plus 1, and then plus 1 times 1. Alright, so I'll get Q minus 1 and plus 1. So you see, my answer is 0. Yeah, so because of the scalar product is equal to 0, so I can know that they are. So scalar product equals to 0, so that's why they are perpendicular. Okay, yeah, you might want to write in full like the two vectors are perpendicular and so on. Okay, so that's the idea. All right, so let's continue with the last question here. Okay, so sorry, this should be 6 as well. Okay, so relative to the origin, all the position vectors for the points A and B are given by OA and OB. So the question wants you to find the angle for OBA. Okay, so make sure that if let's say the question phrase it in this way, right, it will be important for you to check where is your angle first. So to make sure that because when we try to talk about the angle between, right, which means we try to use scalar factor to help us to solve the question, the angle in between, it must be in the form of like either the two, yeah, like what I mentioned just now, the two vector going out or the two vector going in. Okay, so that's why you must need to check the angle here and whether this two vector is the one that you need for you to find the angle OBA. Okay, so we can try to imagine in this case. So we try to make a very simple diagram here. So if let's say I have the angle here. Okay, so if this is O and this is B and this is A, right? So which means I want to find the angle here. Alright, so which means if let's say I want to use the definition of the scalar product to help me to solve this question, so if we try to use the idea for going out, which means I will actually need BO and I will need BA. You get what I mean? So it's the same thing also if let's say you want to draw the going in one, so which means you will need OB and AB. It's just going to give you the exact same answer. Yeah, but I mean normally I'll try to I prefer the approach of like the vector going out from one angle that you want to find lah. So from here then you will be able to find the angle OBA. Alright, then you realize that in this question they give you OA and OB. So which means you have your OB but you don't have your BA. So how are you going to find that? So you need to use the addition that we learned in a previous lesson. Yeah. So now we want to find BA, right? So which means BA will be equal to BO plus OB. So plus OA, I'm sorry. So since we don't have BO, so which means we will use negative OB and then plus OA. Alright, so from here, then let's try to substitute the the column vector that I have here, -1 plus 5, -2, and 4. So let's try to solve it. So -1 is 6, -3, -5. So 1, then 5. Okay, so after I get this, then I have BA. So now I can proceed to find my angle. So I know that the angle, yeah, if you want to write, then you can just write down the angle BOA is actually between the vectors for BO and BA. Okay, so now we are trying to find the scalar product first. So it's the same thing, like go back to like the number 5 there. So how are we going to use the component the scalar product in component form? Then we solve the geometric form. Alright, so let's try to find the BO multiply BA first. Alright, so BO, yeah, it will be easy for us to let us just write down first maybe. We'll be a bit confused here. Yeah, because we have OB here, right? So, okay, so you can just write down first BO is actually 1, -3, and 1. And then BA is what we have found just now. So basically, you're just going to copy it down. Okay, so now we can try to calculate the scalar product by using the component form. So BO multiply BA, okay, will be equal to, so I have 1, 6, -3, -5, 1, and 5. So from there, then I'll be able to get 26. All right, so now let us find out the magnitude. So for BO, it will be equal to 1 square plus -3 square plus 1. So 9, 1, 1, I will get 11. So for BA, then I will have 6 square -5 square plus 5 square. So I'll get 36 and 25, 25, so 86. All right, so now I can try to put them in the formula already. So which means that BO, BA, yeah, I'm just trying to write my cost in the left hand side, but it's the same thing lah. It's equal to the scalar product. Okay, so just rearrange everything. Try to substitute the info that you have here. So square root 11, square root 86, and cos theta will be equal to 26 that we found just now. So cos theta will be equal to 26 divided by square root 11 multiplied by square root 86. So from there, by using my calculator, then I'll be able to get 33.3 in 3 significant figure. Alright, so I hope that you have no problem in this. Yeah, just try to make yourself familiarize with the formula and so on, and we'll be able to look at because we still have one part on the vector equation. So after you learn that, then when we try to look at more questions, then you'll be able to expose to more questions. Okay, so same thing, you will try to look at more application question in your exercise as well. Alright, so remember to do your exercise, and that's it for the lesson 2. Thank you.